Good day, all trainees. It's a good time that we're having this training module, which is based on wireline logging case studies. It's a follow-up of the week 8 wireline logging training facility. Before we start, we'll have to sort of emphasize here that safety is a number one priority in oil well operations. Anywhere you are listening to this training, be very conscious of your environment. Identify your exit points, identify your mustering points, ensuring all gangways are clear of any obstruction should there be any emergency, and slippage. Having done that, we'll go straight into the course proper. Wireline logging case studies. This training is competency based. You are being trained to demonstrate correct depth control, accurate log interpretation, and disciplined decision making under pressure. In International Well Control Forum terms, this training develops knowledge, skill, and behavior. Failure in any one of these can compromise the well you are working on. We'll consider the first case study, which is misaligned perforations. Misaligned perforations. Casing collar locator error. This is based on an oil well in Delta State. This oil well failed due to an 18 feet CCL misalignment caused by rushed correlation. Guns were fired into shale instead of the proposed 29% oil sand. The result was zero oil production and a remediation sidetrack costing approximately $340,000. This was a human decision failure, not a tool failure. This slide is talking about this gamma ray log, where formation quality is expected. Low gamma ray indicates clean reservoir sand. High gamma ray indicates shale. The correct oil bearing interval was clearly visible. Never perforate without confirming lithology. Depth without geology is blind execution. On this slide, we'll talk about CCL signals, correct versus misaligned. The blue curve represents correct alignment. The red curve shows an 18-feet shift. This occurred because correlation was not repeated. If CCL does not repeat cleanly, stop the job. Depth markers. On this slide, we know some basic truths. Perforation guns obey depth, not intention. If depth is wrong, perforation will always be wrong. So make sure that the actual depth is where you perforate. Run out your perforation operation. Operational and financial impact. This error resulted in zero production and a whooping $340,000 sidetrack. Small interpretation errors can cause major operational losses. Take this, is a key thing you should take home with. The key lessons therefore are this: speed improves efficiency, but accuracy protects the well. Never fire guns without stable, repeatable correlation. Gamma ray logging in cased hole. Casing reduces gamma ray amplitude by 10 to 20%, but curve shape remains the same. Shape matching is the basis of correlation. Gamma ray correlation graph. Match peaks, troughs, and trends. Do not match absolute values. On this slide, we'll establish operational use of gamma ray. Gamma ray is mandatory when CCL is weak, noisy, or unreliable. It is a critical backup system. This gamma ray is a critical backup system. The emphasis here, therefore, is that all trainees should focus on matching peaks, troughs, and trends, not gamma ray magnitude. Like we said before, gamma ray is the safety net when CCL fail. And the lessons to be reinforced here is this: when CCL becomes unreliable, gamma ray preserve depth integrity. We will go straight to case study number 2. Gamma ray recovers lost depth. In a highly deviated North Sea well, gamma ray restored depth accuracy from plus or minus 10 feet to 1 feet when CCL failed. On this slide, we will talk about correlation, gamma ray correlation that saves job. When CCL fails, gamma ray preserves depth integrity. Practical instruction for you. Always cross-check CCL with gamma ray in harsh environments. Stop and escalate if correlation is unstable for the right decisions to be made by the decision makers of the asset owners. Production logging tool overview. Production logging tool overview. Spinner shows velocity. Temperatures show fluid entry. Pressure shows flow behavior. And noise detects leak. Never rely on one sensor alone. Draw points from all of the sensors that will be deployed in any service. Case study number 3, water breakthrough. Water breakthrough. A water cut increase from 20% to 72% was diagnosed using a spinner spike and cooling anomaly, indicating behind casing water channeling. This is the water breakthrough graph. Cooling plus spinner spike identifies water entry depth precisely. Have a look at the graph once more. The main panel here, temperature trace, which is the blue, showing a clear cooling anomaly at approximately 8,950 feet, and spinner trace, which is the red, with a sharp spike at the same depth. Depth axis is inverted to match logging convention. The horizontal dotted line marks the water entry depth, and a call-out label is provided. Bottom insert, the water cut versus time, showing rise from 20% to 72% to contextualize production impact. So just follow through with this graph, understand what this graph portends. Well integrity diagnostics. On this slide, well integrity failures are detected using temperature, noise, and pressure responses. Casing leak. A continuous hiss at 7,340 feet identified a micro-cracked casing in an offshore gas well. Let us see the noise log. Every leak produces sound. Noise logging detects failures. Pressure data may miss at the same time. Look at this graph. This visual is designed to clearly illustrate the diagnostic signatures of a casing leak at 7,340 feet in an offshore gas well. I don't want to make mention of the owners of this gas well, but this is a real life situation. A sharp, narrow spike at 7,340 feet represents the acoustic hiss that noise tools detect when gas leaks through a micro-cracked casing joint. Noise amplitude increases dramatically, creating a strong diagnostic signature. Every leak has a sound fingerprint. Noise logging detects what eyes cannot see. Temperature log. and spinal conformation. Localized heating and erratic spinal behavior confirm casing leakage. When you see this erratic heating, you should just know, and spinal behavior, if both are erratic, is a confirmation that there is a casing leakage. Look at the graph critically. Gas flow warms the casing even when the change is small. Production logging temperature tools capture this reliably. Spinal log, the erratic behavior, which is of course the blue curve. The spinner destabilizes due to gas influx, disrupting fluid movement. This results in intermittent, sudden RPM shifts at the leak depth. Leak depth annotation. The graph includes a dashed horizontal line marking the leak depth. Look at it very well, you see it. And a label box identifying the casing leak zone. Application to case study. This graph supports the training narrative. 1. Problem: tubing pressure decline offshore. 2. Cause: microcrack casing leaking gas into annulus. Communication. 3. Detection: continuous hiss and subtle heating and spinal disturbances indicates this casing leakage. Remedy: straddle packer installation. And the lesson to learn here is that noise tools are essential in integrity diagnostics. Cross-flow diagnostics. This occurs even when well is shut in. High pressure zones feeds low pressure zone. Damages reservoir and production altogether. Case study number 5. Cross flow in shut-in well. Cross flow in shut-in well. Unexpected pressure build-up after shut-in. Spinner movements and temperature contrast. Fade plug identified. Plug replaced and cemented. Lesson here is that run production logging tool in shut-in mode. The graph of cross flow in shut-in wells. The graph of cross flow in shut-in wells. Spinner movements, temperature contrast, and pressure buildup confirm cross flow. Multi-phase flow profiling. Gas accelerates spinner response and causes false high velocity readings. Confirm with temperature and pressure. Case study number 6. We've been talking about the various case studies. This while on the 6th now has to do with gas breakthrough masked as oil. Very dangerous. As a course participant, you should be experienced enough to detect some certain things as enumerated here in this program, training program. High spinner RPM with unstable pressure indicates gas coning, not oil increase. You heard what I said, unstable pressure, not stable. You know, gas is highly compressible, so it can be having fluctuating pressure, very much unlike traditional oil. Gas breakthrough marked as oil. Spinner spike, hot temperatures anomaly, and pressure collapse confirm gas entry. Look at this graph. Spinner RPM increases sharply at 9,150 feet. Gas has low viscosity and accelerates flow, tricking the spinner into reading with high velocity. High spinner velocity does not always mean high oil flow. Gas coning can deceive you as an inexperienced operator. Hot temperature anomaly, the red curve. Temperature rises at the same depth as the spinner spike. Gas entering the wellbore reduces cooling and often raises localized temperature. This confirms the spinner anomaly is not oil, but gas inflow. Pressure collapse, the green curve. Pressure log shows a steep drop at the gas entry zone. Gas inflows reduces hydrostatic support, destabilizing flowing pressure. This matches the operator's field observation of unstable pressure. Production versus pressure inset plot. The bottom graph shows two things. Apparent oil production increase from 1,200 to 1,850 barrels of oil per day. Meanwhile, flowing pressure becomes unstable and declines. This mismatch is a diagnostic red flag for gas breakthrough, not increased oil rates. Take note of that. Case study resolution. Gas coning into the wellbore, that's the interpretation. Corrective action. Reduce choke size to stabilize drawdown. Reduce choke size to stabilize drawdown. Lessons to we all, or you all as trainees, is this. Never trust the spinner alone. Like I said, you always combine all of them. Always confirm with temperature and pressure logs. Case study number 7, failed packer and annulus pressure. Failed packer and annulus pressure. Rising annulus pressure with noise and temperature anomalies indicates packer seal failure. You've seen packer before? Try and identify one. Rising annulus pressure, noise and pressure anomalies at packer seal failure confirmed, packer replaced during workover. And the lesson learned here is this. Early detection prevents casing collapse. More often than not, inexperienced operators in the field, when they don't give attention to these events quickly, because of pressure differential, you experience things like collapse casing with inconsistent IDs down to the zone of interest. Graph of the failed packer and annuli pressure. Like I said, early detection prevents casing collapse and measure workover cost. The main log, depth from 8,600 to 9,000 feet. Red noise curve showing a pronounced hiss at 8,750 feet. Orange temperature showing slight warming at the same depth. The packer depth is marked with a dashed line. Have a peep into this graph by your left hand side and try to identify, look at it very well. Insert A annulus pressure versus days shows a steady rise after shut in, matching the field report. The point here is that try to explain how noise and temperature anomalies at packer depth together with rising annulus pressure confirm packer seal failure. Emphasize early detection to prevent casing collapse and the necessity of workover to replace the packer. If you are proactive enough, the heavy cost of deploying a workover rig because of your delayed decision making cannot come in here. So we should try to be proactive at all time. The final takeaways is this. CCL ensures depth accuracy. GRO, which is gamma ray, provides backup. CCL stands for casing collar locator. GRO provides backup correlation. Temperature identifies fluid entry. Spinner indicates velocity with caution. Pressure confirms flow behavior. And noise detects leak. I would say thank you very much for giving me your undivided attention. So before you go away, go back to that week 8 oil well logging training module, which we discussed. In one of the slides, there is a provision for case studies, and that's why this one is coming to you right now. I wish you all the best. Stay glued to the remaining part of the training. So at the end of the training, you would have gone through all the quizzes and all the course contents, which comprises 12 weeks. You will be issued a valid certificate stating the course modules you've gone through. So when you go to any employer of skill, you will stand out as a preference to be engaged before any other person that doesn't have opportunity to go through these courses. So thank you very much. Thank you very much. Thank you very much.